Hey everybody, Mr. Grove here. It's been a little while since we've talked about the friction worksheet problems, and then with the lab coming up, so I just want to kind of walk you through a little of all of that, and then when we meet back on Monday, we should be good to go. So let's take a look at the worksheet. So first problem was 1,500 kilogram car, constant velocity 30 meters per second. If the force of push of the engine is 2,300 newtons, what is the force of friction? Then also what would be the mu value for the road surface. So we set up our force diagram. So we got a push here caused by the engine, friction, normal, and weight. Since we have opposing forces, we're going to have to choose a plus and minus. So I chose positive as up and forward. So that means down would be negative and then friction would be in the negative direction. So my equations then that I built would look like this. So normal minus weight equals, and the question we always ask is MA or 0. Well, it's not even moving up or down, so that'd be 0, Newton's first law. And then the other one is going to be push minus friction equals, again, MA or 0. And so on this one, we have a constant velocity. So that means Newton's first law would be 0 again. So we know weight is mass times gravity, so I can solve for my force normal here, which would be 14,700 newtons. We know friction is normal times mu, so I can substitute that 14,700 in here for the normal times mu. The push of the engine was 2,300, so that was given in the problem. Solve for mu, and we get 0.156. No unit because mu does not have a unit. It is just a coefficient of friction. So that would be problem number 1. Problem number 2, we had a wooden block pushed across the level surface from rest to 6.2 meters per second in 88 centimeters. So what's the force push in newtons? So we're pushing this block, and it's getting faster as we push it with this constant force. So, force diagram, I chose positive, and just to shake it up, down as positive as well. So my two formulas that I made would be F equals MA here and F equals MA here. So weight was positive minus normal force equals MA or 0. Well, we're not even moving up and down, so 0. And then on this one here, we got push minus friction, push positive minus friction negative, equals MA or 0. Well, in this case, we're going from rest to 6.2, so we're getting faster, so we would have acceleration. So Newton's second law says that would be MA. So force weight would equal normal. We know weight is mass times gravity, so 10 kilograms times 9.8 gives us the weight, which would also be the normal of 9.8. Over here, we got our push minus our friction, and that's normal times mu. The mu comes from our chart we had to look up. Wood block is being pushed across the level surface, so wood on wood, so it would be 0.2 on that. So equals MA, 10, and then our A we didn't know, so we had to kind of go old school here and use the VI, VF, TAD. So VI was 0, VF 6.2, D was 0.88. So that fourth equation allows us to solve for acceleration, and we get 21.8 meters per second squared. So that goes in right there. Okay, and now we can solve for our force push, and we get 237.6 newtons. 237.6 newtons. So that's question number 2. Number 3 is very similar to our lab that we did. So we're sliding this hockey puck across. There's no push. We're not continually pushing it. We released it, and now it's going from 25 meters per second to rest. So I like to keep my friction always negative, so that means the opposite, even though there's not a force there, is positive. And then we had the normal also as positive. So my two equations were this one, equal to 0, since we're not even moving up or down. And then this one, minus force of friction, equals MA Not 0 ma because we are slowing down. So we do have an acceleration even though it's negative. Okay, so this would give us our force normal, because we know normal equals weight, which is mass gravity, time according to our equation that we set up here. So once we get the normal, we can plug that in there. We know that the mu value was 0.1. That was given to us. And so we have our mass times our gravity times 0.1 equals ma. So we can solve for A. Now notice, even though we have mass, notice mass on each side. Mathematically, that can drop out. Don't push buttons if you don't have to. That gives us an A of negative 0.98 meters per second squared, which should make sense because we're slowing down to have the negative. Now we can put that in old school to our VI, VF, TAD. So VI, VF, and A. Solve for D using that fourth equation, and we get 318.9 meters. So again, this one's similar to your lab as we were pushing it, but then releasing it, and it was sliding to a stop. Lastly, we have a steel mass pulled across by a force of 95, acceleration of 1,200 kilometers per hour squared, mu is 0.44. What's the mass of the block in kilograms? And then I also, just kind of for fun, had you, what is the mass in slugs, which is kind of an old-fashioned unit of mass. So set up our equation. So pull positive, friction negative. So that first equation would look like this. And we know it's equal to ma because it tells us we have an acceleration here. The other equation for the vertical, I had normal as positive, so weight is negative, and it's not moving in that direction, so equal to 0. So normal equals weight equals mass times gravity. So we solve for normal, we can plug that in here. So our mass times our gravity times mu gives us our friction. We still don't know the mass though, and we do know that's equal to ma because we have an acceleration. So we have our equation, but a little bit trickier math algebra. So we'll have to solve for m, bring your m over to this side as well, combine them, and we get a mass of 21.57 kilograms, comes out in kilograms. And then just looking at the old unit slugs, one slug is 14.5939 kilograms. I wouldn't expect you to know that, but I do expect you to look it up. And so we would get 1.478 slugs, which is a unit of mass. So that is the fourth equation. So a little bit trickier algebra, but you should be able to do that as you solve for m. Then once we've got the mass, that's enough. We had to convert our acceleration from 1,200 kilometers per hour squared into meters per second. So doing that, our conversion, we know 1 kilometer is 1,000 meters, and hours, so we know 1 hour is 3,600 seconds, but this is squared, so we have to square everything here in the parentheses, including the numbers and units, and so that would turn out to give us 0.0926 meters per second squared that we can use for that calculation of mass. So that's the worksheet. And now let's switch over to the lab a little bit. So the Monday, Wednesday group, your labs kind of looked like this. Tuesday group, I kind of changed your guys and took that off so it wasn't as confusing. But for our Monday, Wednesday, then we only did the one plastic tray, so we didn't have to worry about that either. So remember, you slid it across. We had a VF. We had a distance and we had a time. So if we take our two old school equations, solve them for VI, set them equal to each other, then that will allow us to do some pretty crazy algebra, but come up with this equation here in the blue. That's a derived equation, negative 2d over t squared equals a. That will allow us to, distance, time from your lab, so that will allow you to solve for acceleration, which would be negative, and that makes sense because we were slowing down. So you're going to have an acceleration for each one of these, so 15 accelerations, 5, 5, 5 for the empty tray masses, and then 5, 5, 5 for the tray plus the 1,000 gram masses. So you're going to have 14, or a total of 30 accelerations. All should be negative. So a lot of calculations, but once you kind of get into the rhythm, you can kind of blast through those. Once you know the acceleration, our force equations that we built was that one there and this one here, using this force diagram. And so those force equations, we know normal is equal to weight, which is equal to mj, mass times gravity here. And then on this one, friction equals ma, and I had friction in the negative direction. So that means normal times mu equals ma, negative normal times mu. And over here we knew normal was mg, so we can say negative mass times gravity times mu equals ma. So you know the a value from solving for that with this equation here. You know gravity is 9.8, and you know your mass values with and without the extra 1,000 grams to put in here. And so you can solve for mu. So we're going to need to solve for a mu for each one of those, okay? And that will allow us to ultimately have 30 mu's when it's all said and done. Now, on the percent relative error, what we're going to do is solve for that by taking the mu that we have for each trial, so 30 different mu's, and compare that to the average for each one. So you'd have 5 mu's here. So 5 mu's for your plastic. Average those 5. And so that would be our relative error. So here's our average, then here's the individual mu. So we do that for this trial compared to the average over the mu average times 100 to make a percent, and that will give us our relative error. So that's going to kind of tell us how close that mu value was to the average. Okay, so the relative percent error. And we'll have to do that 30 times. So just kind of get in a rhythm, blast through those, and see how your data turns out. So feel free to clean up the data tables. You can make a new one if you want, because you had a time, a distance, solve for an acceleration for each one, and you had a mu for each one, and then you're going to have a relative percent error then for each trial. Okay, and then ultimately we've got some questions that I will attach to the Google Classroom then that you can answer in addition to just your lab calculations here. So no write-up per se, we're just going to answer those questions and then show your calculations for all of that. So hopefully that will help you get through. If you have questions, shoot me an email, and we'll see you guys on Monday.